Hi, everyone. So thanks a lot for joining, and thanks, Andrea, for the introduction and for inviting me. So I would like to contribute today to this very interesting discussion by sharing my experience on unknown object grasping, and in particular, I'll talk about a possible pipeline to deal with this problem and a benchmark for challenging robotic platforms. All the work I'll present today has been carried out when I was at the Italian Institute of Technology. So just a few words about me. Right now, I'm a robotics research engineer at DeepMind, and my main interests are in robotics, manipulation, and reinforcement learning. Previously, I was a PhD student and a postdoc at IIT, where I used to work with the iCub humanoid robot. And during my PhD, I was also a visiting scholar at UC Berkeley, where I had the opportunity to work together with Sergey Levin and Peter Abil. So I will talk today about the work I have done during my PhD and postdoc at IIT. So we all know that grasping unknown objects is really challenging, and this becomes even harder and harder when we have to deal with limited robotic platforms, which are really common in research. And so in this case, it's really important to have both algorithms to deal with these challenges, coming both from the task itself, but also from the hardware we have to work with. And also it's important to have a fair way to benchmark, to compare algorithms, so different algorithms tested on different robot platforms in order to distinguish between, for example, the failures caused by the algorithm itself and those caused instead by the hardware. And these two will be the topics of my presentation. So let's start from a possible pipeline to grasp unknown objects when we have to use a robot with imprecise kinematics. So the pipeline we proposed consists of these 6 steps. So at first, we detect, segment the object, and extract a partial point cloud of it. We then use this partial point cloud to reconstruct a 3D model of the object and compute a grasping pose. Then the robot can approach the arm towards the object, and at this point, we want to precisely estimate the pose of the end-effector. In the end, we use a visual servoing to precisely reach for the final grasping pose, and then the robot can grasp and lift the object. In particular, I'll focus on the 3 main steps of the pipeline, which are the object modeling and grasping pose computation, the estimate of the pose of the end effector, and the visual servoing. So let's start from the object modeling and grasping pose computation. So for doing this, we use Superquadric functions, which are the generalization of ellipsoids. So basically, with just 5 parameters, we can represent a lot of different 3D shapes. You can see here all the shapes that can be represented with Superquadrics. And the good thing of Superquadrics is that we can reconstruct the Superquadric fitting a partial point cloud just by solving an optimization problem, whose cost function imposes at the same time the minimization between the distance the minimization of the distance between the points of the partial point cloud and the surface of the ellipsoid. And also, it minimizes the volume of the superquadric because we want to find the superquadric, the smallest superquadric that can fit this partial point cloud. We decided also to represent the volume graspable by the hand with an ellipsoid, and then we used these 2 models, so the object superquadric and the hand ellipsoid, to compute a grasping pose. Also in this case, we use an optimization problem, and in particular, the cost function imposes the overlapping of the hand ellipsoid on the object superquadric, and instead we use the constraints to impose the reachability of the pose and eventually also some obstacle avoidance. So in particular, in our case, the only obstacle we consider is the table on which the object is located. You can see here some example of reconstructed object models and grasping poses. Okay, so now we have a good representation for the object and a grasping pose. Let's see how to properly have estimated the end effector pose. Why do we want to do this? So the ICAP is affected by an imprecise kinematics. You can see from this video that there is a significant mismatch from what the robot sees and what the robot feels, perceives through the kinematics. So the skeleton in this video is obtained by using all the encoders of the robot, and you can see that it's not perfectly overlapped on the arm in the image. So for this reason, we decided to estimate the 60 pose of the robot End-effector using the robot cameras. And for doing this, we base on recursive Bayesian estimation, and in particular, we use a particle filter. So the high-level idea is that for each particle of the particle filter, we render an End-effector image as it would appear from the robot view. And for doing this, we use the robot CAD model. And then we use the state representation to directly estimate the 60 pose using 2D image descriptors. More in detail, so starting from the top left corner, we have that we sample particles as particle filters does, and then for each particle we render an End-effector as it's seen from the robot cameras, and then for each of these rendered image we compute the histogram of oriented gradients, which are the features we will use to compute the update weights. And in particular, in this case, what we want to do is to compare the hog coming from each rendered image with respect to the hog coming from the camera image. Then, of course, we can follow the standard particle filter updates, and we can also extract an estimate of the pose of the End-effector. You can see here in the image, this is our estimate, and of course, it's overlapped on the robot image. Okay, so we now have a grasping pose and also a precise pose of the End-effector, so we can reach for this pose using visual servoing. For visual servoing in particular, we solve two decoupled image-based visual servoing problems. In one of these, we solve for the translation motion, assuming the rotation is completed, and in the other, we compute the rotation motion under the assumption of achieved translation. And this gives us very smooth trajectories thanks to the redundancy of the ICAP arm. Okay, so this video shows at first the execution of the pipeline without the visual servoing and the estimate of the End-effector pose. So here we have the object model, the grasping pose computed, and all the movements are now executed in open loop. And you can see, for example, when the robot is reaching the final pose, the pose was not so precise, so there were some offsets, and in fact, the robot just pushed the object and the grasp fails. Now we will see instead the execution of the entire pipeline, so also including the estimate of the pose of the End-effector and the visual servoing. So here we have the same object model in grasping pose. Here we are using the particle filter to estimate the grasping pose of the robot arm, and then thanks to our visual servoing, we can better precisely reach the final grasping pose, and then the robot is able to grasp, so close the hand, grasp, and lift the object. Okay, so this is an example of a possible pipeline to deal with a challenging problem and a challenging platform. And it's really, it's evident that it's a really complex pipeline when you have to deal with complex problems, and complex robotic platforms usually are made of several steps. So we really need also a way to fairly compare algorithms that are tested on different robots. And for doing this, we propose GRASPA. And GRASPA is a robot arm grasping performance benchmark whose goal is to distinguish between the failures caused by the algorithm itself and those caused by the hardware. So GRASPA provides 3 grasping scenarios made with a subset of YCB objects and of increasing level of difficulty. And we also provide printable layouts. You can just download, print, and put in front of your robot to reproduce the grasping scenarios. In GRASPA, we also want to assess the robot reachability and the calibration of the vision system within the grasping layout. We also propose to use a grasp quality metric to evaluate the candidate grasping poses in simulation, so before executing them on the real robot. We also include a score to assess the grasp stability. So once the object is in the robot arm, we want to check how stable the grasp is. And all of this can be done in isolation or in clutter. And we also provide a composite score to quantify the overall performance. I'll now show you a video with an example of application of grasp. So at the beginning, so these are, for example, the 3 sets of poses we ask the robot to reach in different regions of the layout. And the robot reaches for all the poses, and we collect the reached poses using the kinematics. So you can see, for example, for the eye curve, that so on the left, you can see the target poses, on the right, the reached poses. And for example, the ICAP was not able to properly reach some of the poses. So we won't take into account the objects included in those regions of the layout, because if the algorithm fails, it might be that the reason is the hardware and not the algorithm itself. We then do the same for the calibration of the vision system. So also in this case, we ask the robot to reach for all these different poses, but in this case, the reach poses is collected using the camera and not the kinematics. So GRASPA also includes the possibility to select only those objects which are really graspable by the robot. For example, in this case, we discarded the hammer because it's too heavy for the ICAP to be grasped and lifted. And you can see, for example, for the ICAP also other objects are not graspable. Okay, after this inside, we can also evaluate the let's say ideally how good the grasping pose is. So we just use a simulation and a simulator for this. And once we have a good score, some scores in simulation, we also execute the grasping on the real robot. And then we want to assess the stability by asking the End-effector, for example, to rotate the wrist to see how stable the grasp is. And in the end, what GRASPA provides is a table with all these scores, and also a composite score that takes into account the overall performance of the pipeline. But in this case, we can, if the performance, for example, are not so good, we can see if the reason is the algorithm itself, or for example, the reachability of the robot, or other possible sources of failure. Okay, so in summary, I'll talk about a possible approach for grasping of a known object for robots with limited, for example, limited hardware, and also a benchmark in order to fairly evaluate algorithms tested on this. And in particular, the pipeline I show consists of a Superquadric object modeling and grasping, the End-effector pose estimation using a visual particle filter, and then an image-based visual servo. So that's all. Thanks for your attention. And if you have any questions, I'm happy to answer.
Thank you. Thank you, Giulia. Thank you very much for your presentation.